Hello everyone, like Pet said, I will be presenting you how to prevent enlargement attack on ranging systems. Like ranging system is like well studied and people are working on it, and there are a lot of already use cases and the use cases are increasing rapidly. For example, access control, asset tracking, localization, robotics, all these applications need ranging in some sense. The way forward for the localization for these applications for secure ranging is ultra-wideband, and standardization and commercialization efforts are going on. Like a lot of people and a lot of money is getting invested in these kind of ranging systems, to build these systems, to design techniques how to secure these systems. However, there are still possibilities that an external attacker can prove that the distance measured is measured incorrectly because of the presence of an attacker. So what are these issues? What can an attacker do in this scenario? So we look at two possibilities. Either attacker can prove that two devices are close to each other when they are actually far from each other, like in the PKES system, where the key is inside the house, car is parked outside, but attacker can prove that the key is near to the car. Or there can be distance enlargement attack, where the devices are very close to each other, but attacker prove that these two devices are far from each other. This can lead to like maybe possibly collision, like if two vehicles are going one after another and they measure a wrong distance between them, they might speed up and collide, or they measure the wrong position of themselves and like start taking a wrong path. Until now, the community has mainly worked on preventing reduction attacks. However, there's not enough work done on enlargement attacks. Like we don't want systems to collide or follow a path which is designed by attacker. So how are these systems look like today? So to prevent distance reduction attack, we use challenge response protocol, where these challenge and responses are generated cryptographically. So to manipulate the distance, the reduction attack, for the reduction attack, attacker will need to predict these challenge and responses. Given that these are cryptographically generated, attacker cannot predict them in advance, so he cannot perform distance reduction attack. However, that is not entirely true for the enlargement attack, because this signal is already being generated, this packet has already been sent, and then attacker is trying to do that. So attacker doesn't have to break any cryptography at the present moment. So attacker can just cancel this signal, or he will just replay the signal with higher power later in time and create an effect at the receiver that it calculate time of flight on the attacker signal and not on the legitimate signal. So we need something, we need a kind of challenge response protocol which is secure against the enlargement attack. So we need to design secure challenge responses to prevent enlargement attacks, so that the time of flight estimation is done on the signal transmitted by the legitimate transmitter and not by the attacker. So over here, like we already know that we have to design these challenge response protocol. Now I will go more into the detail of ultra-wideband, like how the physical layer of ultra-wideband looks like, how the attack is performed, and what are the ways in which we can prevent enlargement attack. So physical layer of ultra-wideband can be modulated by using on-off keying modulation. Over here, the presence of pulses in initial part of the symbol represent bit 1, and the presence of pulses in the later part of symbol represent bit 0. So when this signal reaches at the receiver aggregate energy of these pulses. So if the initial pulses have higher energy as compared to the later pulses, this is detected as bit 1, otherwise it is detected as bit 0. So how will an attacker perform enlargement attack on these kind of bits? So here we have two bits, bit 1 and bit 0. I think it's wrong. And then attacker can simply relay this signal after time delta. And given that this signal attacker is relaying with higher power, it might be possible that the receiver log onto the attacker signal and calculate the time of flight using this signal. Or there can be even severe attack where attacker first try to annihilate the legitimate signal and then replay this signal. So even if an attacker do something smart, it still has to look whether there was a legitimate copy of this signal or not. Or there can be just relay attack where two devices are not in the communication range, or the signal is being blocked by a wall or something, and the receiver is receiving only the copy of signal which is generated by attacker. Out of all these, annihilate and replay is most severe kind of attack because attacker tries to annihilate the legitimate signal and send the copy of signal later in time. So even if a receiver perform back search over this signal, he will not find anything because it is just not available on the channel. So we can say that just generating secure cryptographic data at the higher level is not enough to prevent enlargement attack. We need to perform attack at the physical. We need to perform checks at the physical layer. So first of all, we have to limit that we can only achieve secure systems which are secure against distance enlargement attack if these two devices are in communication range. So if legitimate signal is not getting received at the receiver, there is no way of detecting this signal. So this is our first assumption that these two devices are within the communication range, and if they are in communication range, they are able to communicate with each other, and this signal is getting received at the receiver. And now attacker have to prevent this reception. So like if the signal was generated by just on-off keying modulation, it wasn't enough. So how do we generate these code which can be used to prevent distance enlargement attack? So here we show a code structure. Here we have alpha pulses. There are beta positions where we don't have pulses. This can be considered as an on-off keying modulation scheme because over there also we have some positions which have pulses and which doesn't have pulses. But before transmitting this signal, we randomly change their polarity. And after changing their polarity, we reorder these pulses. So changing polarity is not a problem for our receiver because our receiver, as we have seen earlier, it is an energy detector receiver. An energy detector receiver just accumulate energy. It does not care about the phase of these pulses. And these pulses are separated by time Ts, and this is more than the round trip time of the signal for a maximum communication range. So what's the difference between when we are sending this signal and what we are receiving? So signal is degraded during transmission. There will be some noise. There will be, the attacker will be trying to distort this signal by sending a cancellation signal, and attacker will certainly replay this signal to affect time of flight estimation. Now, when this signal will reach at the receiver, it will start searching for this code or signal we are sending. Most probably, it will log onto the attacker signal because it has higher power. But if it search back, it might find copy of the legitimate signal which has been distorted by the attacker, or it might log onto the noise. So whatever we do at the receiver, we should not discard authentic signal as the noise, or noise should not be detected as an attack. So this is what we do at the receiver. So I will not go into this complex way of doing it. Just look at the takeaway we have here. The total energy we are receiving should be less than certain threshold, and this signal should not be similar to expected code, and then only attacker can win. Because if attacker add too much energy into the channel, we are saying that this signal will be used for time of arrival estimation, and if the signal is similar to the code, then we will obviously use it for time of flight estimation. The code structure we have designed here sort of prevent attacker to achieve these two objectives. Why? Because of the random polarity and random position. So if attacker guesses the polarity of the pulse incorrectly, instead of annihilating this signal, instead of cancelling this signal, the attacker will increase energy of this signal. If attacker does not get position of the symbol correctly, he will add energy into this signal. So let's see what will attacker do. We have our signal. After degradation, let's see, this was the signal we were expecting. Attacker tried to send a signal with same energy, but he does not know the phase of these pulses. He does not know the position of these pulses. He will just randomly send them at some places. Why does attacker does not know the phase of these pulses? Because these pulses are very, very narrow, and this is hard for existing receivers, or if the attacker is out of line of sight of these devices, to know what exactly the phase of these pulses is. So it is hard for attacker to know the phase, it is hard for the attacker to know the position. So attacker will just randomly send pulses at certain positions. If attacker is lucky, he might succeed in cancelling some of these pulses. Otherwise, he will either amplify the existing pulses or add energy at the positions where energy was not expected. And given that amplitude is increasing, the energy increased further. So this was our authentic signal. This was supposed to be received, like there will be some positions which have energy, there will be another positions which does not have energy. And this is how our code should look like. But instead, after attacker tried to annihilate this signal, instead of annihilating this signal, attacker have added energy at the positions, like even more energy at the positions where energy was present. He also has added energy at some positions where energy was not present, but still the code structure looked very similar to what was expected. So we can say that attacker, it is hard for attacker to achieve this goal of not increasing the energy too much and still changing the code structure. To analyze this, we use a probabilistic model as well as performed simulations. So let's look at the probability model. So over here we know that there are two objectives attacker has to achieve, like total energy of the signal should be less than certain threshold, and the similarity of the code to the received signal should be less. Then only attacker can succeed. The probability of attacker success depend on different factors here, like code structure, how many pulses are sent, how many positions are there which doesn't have pulses. So what is the formation of alpha and beta? Then there is a aggregation function which decide on like how many pulses of each bin beta and bin alpha are taken to compare the signal. So basically this is used to detect the similarity between these two codes, the received one and the expected one, and the number of pulses transmitted by the attacker and the channel condition. So over here, we see that on the x-axis, we have the number of pulses generated by attacker, and on the right axis, we have the probability of attacker success. And over there in the zeta, for the two different lines, it basically shows like how much far, like how much degradation of our actual signal happened. So how much far our actual signal is from the threshold. So attacker have that much amount of energy he can add into the channel. So so by using the number of adversary pulses on the x-axis, we show that if attacker keep adding energy on the signal, then he violates first condition. Otherwise, he does not succeed in the second condition. So he cannot achieve these two goals simultaneously. So to achieve the second goal, he has to violate first goal, and to achieve the first goal, he does not succeed in achieving the second goal. So over here, we show that these two goals cannot be achieved simultaneously. We also, to simulate the, to get the feel of like how this system will work on the real environment where the noise is present and there might be interference, we simulated it using the channel model which are provided by IEEE, and we show that this system works at different distances and the probability of attacker success is same as the one we have calculated in using probabilistic model. We show that distance enlargement is a big problem. We needed a scheme to prevent those attacks. UWB-ED is the first scheme that prevents distance enlargement attack. Thank you.
Questions for our speaker? So one question I had from your talk is you've done a lot of experiments to show that this provides the security guarantees that you're looking for. One of the things I noticed, though, is that you are moving the pulses around in time, and I was wondering if that might have an effect on the function of the applications that this is going to be used for.
Oh, you mean over here, right?
Yeah.
Yeah. So, like it will not have any effect on like system performance, like where the pulses are present, because the transmitter and receiver share this information, like where the pulses will be present and where the pulses will not be present. So, like receiver can compare like whether the received signal is similar to the expected one or not.
Sure. I just meant if it was going to take longer to get a range finding, for example.
Yes. So if you have to add a lot of free spaces, then for sure it will take longer time to do the ranging. Yeah.
Great. One more question?
One, yeah. So for the distance enlargement attack, you said that the attacker would have some hard time locating the pulses or determining the phase of those pulses. And so it was not completely clear why is that the case, and especially that in this type of attacks, it's not like a real-time attack, let's say, because the attacker has some time to process the signal and try to analyze it, etc.
Yeah.
So if you can clarify that.
Yeah, sure. So over here, over here we said that, okay, we will have like a signal which have like some pulses at some positions and not at another positions. So attacker doesn't know where these pulses are present, and these pulses are very, very narrow. So like 2 nanoseconds. So attacker will have hard time in detecting the phase of these pulses, and and even the pulse is present or not. And for the 2 nanosecond, attacker has to be really in the communication range of these two devices. So he has to really sit on the antenna of one of these devices to do this attack. Otherwise, he cannot detect that. And the and the benefit of doing this is that attacker need to know the phase of these pulses to achieve cancellation, but receiver doesn't care about the phase of these pulses, because receiver just take energy of these pulses and then aggregate it.
Okay. So aren't these signals, part of an error correction code or something, or are they just randomly generated signals? Because if it's part of a code book, then the attacker would have more information on where the pulses should be.
Yeah, exactly. That's why we say that we use this reordering. So this is a kind of a pseudo-random reordering, you can say. And the transmitter and receiver share this information, but this is not generated using any code book, because attacker can also have access to that code book, and we don't want that.
Okay,
Thank you.
Let's thank our speaker one last time.